Okay, another criticism I got from Reddit in my June 2022 update of my designs for this robot was people were saying, like, you shouldn't be using 2430 motors, which is like the main motors I'm using all throughout here for actuating the robot's fingers and wrists and stuff. I do switch to some bigger motors for like the biceps and triceps and stuff and shoulders, but 2430 you'll see probably more in my robot than anything else. Occasionally you'll see bigger ones, but most of them, like this, all of these, they're all 2430. Most of what you see in here are 2430. Then occasionally you'll see a big boy like that, um, and that's a bigger one. But this is 2430. This is 2430. That's a bigger one. Anyways, so 2430 was criticized because it's for drones and it's not the highest torque right out of the box. But it's $11. It's 5800 kV, and so that means like it's going to be really really fast, and its low end torque will be kind of minimal. Um, but that's what down gearing is for. So basically, yeah, if you can get a lower kV motor, that's ideal. But the problem is when you do that, 24 represents the diameter and 30 is the length. So your can size, if you want like a high torque motor, becomes like two or three times this, and then it's like this tall. So it becomes like a big, like hockey puck instead of like a pop can as far as that dimensions. And we want long, thinner motors because of the form factor we're trying to fit stuff in. So if you look at this here, you can see like this is just barely fitting in here without. Yeah, it just barely fits. It's touching almost the outside of this forearm, and it's almost touching the bone. That's like a perfect fit for that motor, and that fits in this form factor that we're working with. What happens if I take that guy's advice and use a high torque, like a gimbal motor, like he was saying, with the much lower kV? It's like, yeah, I get it. You want to only have a 3-to-1 gear ratio, so you save on gear cost and complexity and whatever, right? By having a motor that's already um, torque to begin with. That's kind of the idea behind using like a gimbal motor with low kV. But those low kV motors are not very popular, so they cost a lot more and harder to get your hands on. There's not as much variety in them. Okay, is this good? Yeah, okay, good. Quite vertical. So it's going to be like this. All right, so tell me, how are you going to fit that in the robot's arm? Like, you wouldn't be able to fit that anywhere. If it's like this, that'll be sticking out. That's going into the bone, so it need to be like this. How's that going to fit? That's not going to fit. So, where do I put this thing? You guys can see clearly it just doesn't fit with where we have our muscles in the human body. Um, that's not going to work. That's sticking out. It needs to fit inside the form factor of the human body. Remember, we're trying to make it look human like, so it can't have anything sticking out. That won't work. So it literally won't even work in the beefiest part of the arm. So what? You got to put one like right here, and then that even won't work. It's like when you put that bone in, of course. I don't have it in this model right here, but so basically, maybe if you like did this, you could maybe get rid. That doesn't even work. Even when I got cheeky, it didn't work. Wait, it could. Could it work here? No, that's even going through the bone. Looks like we were able to make it fit like barely one time like that. Okay, so we might be able to. Oh, you know what though? When this pronates, basically that would not work because of how the pronation works. Um, so check this out. This goes like this when the pronation occurs. Um, this rotates like that. Like if you picture that and that being a leg, it's like you cross your legs, so you have to pee. It's doing that. That's how the pronation of the bones works for rotating the hand in the like toward the thumb going toward the body, like rotating your hand. That's how that works, and that would actually, if you see here, it would stop it from pronating. It's now going through the bone. So you couldn't have pronation anymore. So even that cheeky solution would not work. Whereas this doesn't affect the pronation at all. And so what's the difference between these two? Well, this motor and this motor, let's just think about this a little bit as far as like what is the real difference. So obviously this motor is much more suited for fitting tons of them into like these form factors that you find in the human body around bones. You think of the shape of muscles, they're usually elongated sacs, and these motors need to fit wherever the muscles are fitting. So these need to be elongated sac shaped. And so that's why they're ideally suited with this type of can ratio where it's like 2 to 1, or it's like 1.75 to 1 ratio to length to width. Whereas this is kind of like 1 to 1, 1 to 1. It doesn't have the elongated. It's like big in this direction, big in this direction, big in this direction. It's like a big box. It pretty much, as far as form factors go, it's like a cube. It's like one big, ugly cube. So there's your gimbal motor form factor compared to this thing's form factor, which is more like something more like that. So you can see the form factor of this fits in this type of volumetric box, and then the form factor of this fits in this volumetric box. And this kind of shows you why gimbal motors are so bad, because that is not the shape of muscles. This is more so along the shape of muscles. And you can fit a lot of these in a row in the same amount of space taken up by an actual muscle. So that's why this type of form factor is good. So this is not a high torque form factor. This is. This is high torque, probably largely because it could fit bigger magnets or something, and just the way it's wound up, um, it just makes more torque. But look at how huge it is in every direction. It's just big. Um, Whereas this is not. This is just perfect form factor for a robot. That's why we have to go with this route. Now, as I was saying before, this will have much higher torque and lower speed. This will have much higher speed and lower torque. Now this thing's torque, even stock, it's not going to be enough torque. You still need to down gear it, but you don't need to down gear it as much. When you're trading speed for torque by down gearing, and we down gear by way of an Archimedes pulley system for my design, instead of actual gears like bronze gears. Um, the word down gearing is almost not satisfactory for what we're trying to describe. We're downshifting, but down gearing is the only word I know of in the English language. But when you say down gearing, it has the implication of using actual gears. We're using pulleys. When you down gear by way of pulleys, it should be called like down pulleying or something. If you say down gearing, it makes you think, well, are you using gears? No, I'm not. So that's kind of deceptive and confusing that we don't have a better word than down gearing, but I digress. So this has to be down geared maybe like only 3 to 1, whereas this might need to be down geared 50 to 1. So the gearing solution for this has to be more extensive, but the two can output finally the same speed and torque after the gearing sorted. This will just require less gearing to reach the desired output torque and gearing. This will require more down gearing to match this thing's torque. And so when you look at my gear system, this Archimedes pulley style gears, you'll need more of these down gears. This is 2x the torque and 1/2 the speed, 4x torque, 8x torque, 16x torque. That's how the math works when it's this type of gearing system. 16, then we go 32, and then 64. So 1, 2, 3, 4, 5. If we use 6 pulleys, we'll get 64 to 1 gearing, and I think that should be sufficient. So this will be 64x, whatever its original torque was, it'll be 64 times that torque after we're done gearing it, down gearing it, and it will be 1/64th the original speed. So we trade speed for torque by gearing. This one, since it starts out with higher torque, might only need 3 to 1 ratio, or 1 to 3, or however you do it. Yeah, 3 to 1 ratio. So it would be 3x the torque that it normally puts out will get you to your desired torque, and then you're trading speed for torque with this too, but not as much so. So that's really the extent of the advantage this gives, is you just don't need as much gearing. And then it comes down to both how much total wattage do they both run. If this is a higher watt motor, then obviously it's going to be a little bit stronger. And if it's a much bigger can size, it might have bigger magnets and whatnot, so it might be stronger as well. But as far as if you take 1-to-1 can size, the total strength per can size should be similar after the down gear is accounted for. So you're not really gaining much here with the gimbal motor compared to a higher kV motor, other than a need for less gearing. You don't have to worry about gears as much. But as I showed you, this does not fit well in a humanoid robot form factor. This got popular because they put this inside, like they design it into the elbow joint or into the knee joint of a hinge-based robot framework type system, not a ball and socket type system that uses human skeleton design. It would not be able to be built into the joint itself like they do sometimes with these. And I guess sometimes people get away with using these without even gearing at all because they're so high torque right out of the box. And so that's kind of a nice thing. But for a project like mine, where we're not able to build these into the joints, they just have no place. So they're not even a viable option because of this. The form factor is disgusting compared to what we want. And these are not such a curse when their form factor is so excellent, their strength, their efficiency, everything's very good, they're quiet, they're powerful, they're fast, and whatever excess speed they give you, you can trade speed for torque via your down gearing or down pulleying system. So that's not an issue. That's solvable very easily. So that's why gimbal motors or high kV or low kV motors with much larger diameter can size is not a viable thing for the robot. And you'll note that they're also not very popular for RC or anything else. The popular ones all have the can size. These are the can sizes that were for sale on eBay that I selected. And this is the most popular 2430 that I'm using the most on my robot for most of the robot's muscles. And these other ones have similar form factor. In fact, this one I can't even use. It turns out this is an outrunner, and I can't use outrunner. It has to be inrunner. Outrunner means the can rotates. We don't want that. We want just the inner shaft. We want this part to rotate, and this to all be stationary and strapped to the robot. So this is inrunner style. This whole thing rotates, and then a little band right here stays still, and then this rotates along with this big can section. It's like cut right here, and this whole thing rotates. That's no good for what we want. So our biggest motor we'll be using on the robot for like the quadriceps is this, and this is called a 4082. So it's 40 millimeters wide by 82 millimeters length. It's a $65 motor, inrunner style, 1/7 RC motor, 930 kV. So that's a much more reasonable kV. It's closer to like the gimbal motors that people wanted me to use. 3,400 watts. That's so amazing, isn't it, guys? That's going to have some real power. It's got to. Because, you know, if it's efficient and it's actually using, if it's actually converting that wattage to motion, that's a lot of wattage. That's each circuit of a house is 120 volts times like 10 amps before it blows the fuse. So that's 1,200 watts for a circuit. This is the equivalent of 12, 24, 36, about 3 circuits. That's like 120 volts, 30 amps. That's like 3 full circuits of a house would be required just to run this one motor. That's got to be insanely strong. I'm so excited to see how strong this is. Once you down gear and everything, it's going to be like insane. And using 4 of these just for the quadriceps of the robot, people don't think that's going to be enough. I think it will be enough. But no, I have not like perfectly done all the math. It's like people don't realize. Another thing, like I did some of the mathematical calculations for like some of the servos and stuff for like the finger or whatever. I was doing that in some of my earlier videos. You guys can check the videos to see proof. I was doing math. People are criticizing me for not doing math for every single motor I put in here. All right, and just a little evidence that I did in fact do calculations for torque and leverage for humanoid robots. Early on in my project, I did the math. You can find that in my 9th video, calculating leverage and how it applies to robotic joint actuation here. And I run through the concepts and I show some of the mathematical formulas and proportions and stuff, and I actually calculated things. And there might be some follow-up videos also around that time where I discuss this a little more. So the people on Reddit who were saying I didn't do any of the math and I just picked brushless DC motors at random without any thought put into it, that's just not true. They're just making stuff up. They don't know what they're talking about. But it's because once you kind of get the idea of how big of a motor you need, we were able to establish earlier that even like a much tinier motor than what we're using would actually work with the down gearing for the fingers. The MG996R is about 1/10 this amount of total power as the motors we're using now, the 2430 motors, the brushless. And that was going to be enough. So imagine if we get similar down gearing and a 10x the strength, it's going to be 10 times what we needed. So once you have that established, you're like, I know these are going to be good for the fingers and the wrist because I know the relative strength of what my wrist produces versus my fingers. And so then everything becomes relative. Once you have like some muscles figured out as far as muscles to motors ratio of strength, then as you do the rest of the muscles on the body, you can go by size of the muscle. So like the size of one forearm muscle compared to the size of a thumb muscle might be like 3 times the total muscle volume. So you're looking at the muscles volumetrically. And if you're like, okay, that's 3 times the total volume of red meat as this thumb meeting inner thumb. The meat on my thumb is about 3 of these, like the muscle that would be right here. And when you're looking at the pictures you can see that's about 3x the size of that thumb, so it will need a motor, like either 3 thumb motors or it will need like 2 thumb motors. If you think 1 thumb motor is already overkill for the thumb, you'd maybe just do 2. So you'd assign 2 motors for that one muscle. Or you go up to the next size, like a bigger motor that's about double the strength or triple the strength. And so you're basically like, this is about the equivalent of 4 of these as far as wattage going through it. So if you're looking at the watts stats, if you're like okay, this one is 1200 watts and it's a 3660 motor. And if you compare that to your 2430 motor, which was 200 watts, it's 10x the watts. So you're like, yeah, that's going to be at least like 3 or 4 times the strength at the end of the day. And so that can give you just some idea. Between the can size and the wattage, you can get a feel for this will be at least 3 or 4 times the strength. And so if you have a muscle that's total size and volume comparatively to the one you've already established a working motor for, you could say, yeah, that motor will be sufficient because it's going to be like 4 or 5 times the strength of that. And so then you'd be able to select it even without doing extensive calculations for that specific muscle and then somehow calculating how much actual force is created by that muscle on the human body and then calculating everything about that motor, everything about that muscle, some extensive calculations. You know, we had to do a lot of muscles here, guys. So every time you see a motor, we had to look at anatomy of the muscle, figure out what are its attachment points, what's the size of it, what does it look like, and get an idea based on looking at the volume of the meat of that muscle, how much power that muscle has. The meat volume to muscle power is going to be a ratio that can be relied on. So you can visually see how strong a muscle is based on how much meat is there. And so based on just visually comparing everything through those ratios of volume and through the volume of the way the volume of the motors compare, like this one is about 5 times the size of this, so this will be about 5 times the strength of this motor. If they're all things equal, when you can get those types of ideas down, and then you can compare the actual size of the physical pictures of muscles to one another, then you can get an idea for what size motor relatively to another motor you've already selected that you know will work. So you don't have to do the math extensively for every motor. You can do visual math. So when people criticize me for just picking by instinct, that's not fair. It's not just gut instinct. There is a lot of visual measurements going on and estimations based on the visual size and relative strengths that correlate to the size, and then the visual size of the muscle and the relative strength that correlates to the size. You can figure out relatively what size motors you need based on all that. As long as you have a good baseline of knowing some motors and what about their muscle size equivalency will be. Once you've at least calculated some of them, the rest are just rinse repeat. Like you know that the muscle needed for this joint is going to be the same about as for this. And so you don't have to recalculate every time if all these fingers are about the same strength. You just use the same motor for each joint. So there's shortcuts there. And I feel like people weren't understanding that. They're just assuming I'm just no-braining it. So that should help you guys see also what some of the thought that went behind the motor selections on this and some of the thought behind why we're not going with gimbal motors that are low KV. And though these are high KV, which is not ideal, it's okay. People are freaking out like it just will not work. They're wrong. Once you down gear these, they're going to work great. And I've already shown you guys, this is the form factor you'll see inside those hobbyist servo motors that come in the black box. This is the form factor motor. You won't see motors like that. And these will be brushed instead of brushless. This is going to be like 10 times as strong as what you'll see inside those boxes. And yet you'll see those boxes in robot arms all the time, in the forearms and in the hands. You'll see the box type servo where everything's built in. The gears are built in, the motors get built in, the potentiometer is built in. And nobody's criticizing them for using that. But I use something way bigger and way stronger, and I'm going to down gear just as much or maybe a little bit less than those boxes and achieve way more strength and speed than all those box type designs are able to attain because of the way I'm doing it. And so I'm going to have a much better solution at the end of the day. But this is not acceptable. So that's why we're not using low kV motors like people are saying I should be. And I've been getting like big time criticism, like I'm an idiot for not selecting low kV motors, but I'm telling you guys, it's just not viable. And there's not a necessity to do so. That only will simplify your gearing needs. Your down gearing needs will be less extensive. That's it. But it's okay to down gear more. It's not a big trade off. It's okay to do it. Hobby servo motors, all those boxed motors are 180 to 1 down gear. So that's already very standard to do a lot of down gear. And when I down gear this to 180 to 1, or maybe 60 to 1, it's going to be just as strong, but even way stronger than those box-shaped ones you guys buy. So people shouldn't be criticizing me for not selecting these. These will not work. So that addresses that concern.